So imagine a company, right? They go out and spend, I don't know, $10 million to build this state-of-the-art data center.
Oh, yeah. Concrete, cooling systems, the works.
Exactly. Racks upon racks of high-end servers, a full team of security guards. And then, like 3 months later, they realize their brand new application just isn't getting the traffic they expected.
Which is a complete nightmare for the CFO.
Right. So now they have millions of dollars of computing power sitting there completely idle, just gathering dust. I mean, it's depreciating by the minute. But on the flip side, imagine a startup that spends, well, maybe $200 to rent that exact same computing power for a single weekend.
Just to test out their idea.
Yeah, and if it goes viral, they scale it up instantly. But if it flops, they just turn it off when they're done. No harm, no foul.
And that right there, that $10 million mistake versus the $200 experiment.
Yeah.
I mean, that is the entire premise of the cloud. It's this fundamental shift in how businesses operate.
It totally changes how you manage risk, right?
Yeah. Oh, absolutely. Deploying capital is totally different now. And avoiding those massive infrastructural mistakes is exactly why having foundational knowledge of the cloud is so critical right now.
Which brings us perfectly to our mission today. So welcome to the deep dive, everyone. If you're listening to this, you probably have a very specific goal. You are here to master the AWS Certified Cloud Practitioner exam.
Specifically, the CLF-C02.
Yes, the CLF-C02. And we want you to pass it with flying colors. So we've gone ahead and synthesized a massive stack of study guides, official AWS exam outlines, and, top-tier test prep strategies.
We pulled from places like Dion Training, Tutorials Dojo, Free Code Camp, DV Community, all of it.
All the heavy hitters. But, I mean, we aren't just going to sit here and read you a boring table of contents.
No, far from it. We are going to unpack the actual mechanics of this exam, and more importantly, the mechanics of the AWS cloud itself.
Because you need to know how it actually works, right?
Yeah, exactly. We'll explain not just what these services are, but how they function under the hood and, why a business would actually choose to use them. We're going to break all this complex architecture down into very logical, digestible concepts.
And before we get into the heavy technical stuff, I want to address something that came up constantly in our source material.
The target audience for the exam.
Yeah. A lot of people taking this exam are, well, they're project managers or sales professionals or executives. I mean, they aren't software engineers.
Right, and they shouldn't feel like they have to be.
Exactly. The AWS documentation explicitly states that this exam targets individuals with up to 6 months of exposure to the AWS cloud. So you do not need to know how to write code.
You really don't. You don't need to architect some massive global database from scratch.
And you definitely don't need to be troubleshooting Linux server errors all day.
No, it's really about foundational business and technical literacy. I mean, the goal is for you to be able to sit in a meeting with a team of cloud architects and actually understand the vocabulary they're using.
Right, like understanding the risks they're trying to mitigate.
Yes, and the financial implications of whatever design choices they're pitching.
Okay, so before we can even talk about data centers and servers, we need to talk about the battlefield itself. We have to understand the mechanics of the CLF-C02 exam and how to actually study for it.
Because if you approach this like a traditional college midterm, you're going to have a really bad time.
A recipe for failure, honestly. So break down the format for us. What are we looking at?
So the format is very specific. You have exactly 90 minutes to answer 65 questions. But here is the psychological trap. Only 50 of those questions actually count toward your final score.
Wait, really? What happens to the other 15?
They are unscored beta questions. Basically, AWS is constantly developing new questions for future exams, right?
So they're testing them out on you.
Exactly. Before they trust a question enough to let it impact someone's actual score, they test it. They mix these 15 beta questions seamlessly into your exam to see how a broad range of candidates perform on them.
Man, I can see how that would completely derail someone's confidence. Like, you're cruising along, you're feeling really good, and suddenly you hit a question that uses terminology you have never seen in your life.
Or asks about some highly specific, obscure edge case.
Yeah. And the immediate reaction is just panic. You sit there thinking, oh no, I studied the completely wrong material.
Which is exactly why you need to know they exist going in. When you hit a bizarre question, you have to mentally categorize it. Just tell yourself, okay, this is probably a beta question. Make your best educated guess and move on.
Right. Do not let it spike your cortisol levels.
Exactly. Keep you cool.
So let's talk about the guessing part. The questions are a mix, right? Some are multiple choice, so like one correct answer and 3 distractors.
Right.
And then some are multiple response, where you might need to pick, say, 2 or 3 correct options out of 5 or 6. What happens if I am just completely stumped on one of those?
You guess, period. There is absolutely no penalty for guessing on this exam.
Oh, that's huge.
It is. An unanswered question is scored as incorrect, and a wrong guess is scored as incorrect. So you literally lose nothing by trying.
So the golden rule is literally never, ever leave a blank.
Never. Even if you have to blindly pick option C with 10 seconds left on the clock, just do it.
Good to know. Now, for the scoring itself, from what I read, it scales from 100 to 1,000, and the passing threshold is a 700.
Correct. And nobody sees your actual score later. A pass is a pass.
But the stakes for failing are surprisingly high, aren't they?
They really are.
Yeah.
If you fail, AWS imposes this mandatory 14-day lockout period before you are allowed to retake the exam.
And you have to pay the full exam fee again.
Right. And that 14-day window is an absolute momentum killer. People get discouraged, life gets in the way, and they end up putting off the retake for months.
Yeah, that makes sense. The consensus across the DV community guides and all the practice test platforms is that you shouldn't even schedule your exam until you are consistently scoring between like 75 and 80% on timed practice tests.
You really need that buffer.
But how do you actually get to that 80%? I mean, is cramming the weekend before going to cut it?
Absolutely not. Cramming is the worst possible strategy for cloud computing because the terminology is just so incredibly dense.
So what's the alternative?
Well, the Dion training materials strongly advocate for a 30-day or 60-day structured plan. You have to remember, the human brain consolidates complex technical information during sleep over time.
So it's about consistency.
Exactly. Studying 1 hour a day for 30 days builds infinitely stronger neural pathways than studying 10 hours a day for 3 days straight.
Makes total sense. And regarding the video courses, whether you're using Stefan Merrick, Andrew Brown, or whoever, passive watching is pretty much useless, right?
Oh, totally useless. If you treat it like a Netflix show, just laying on the couch, the information is just going to wash right over you.
So how do we fix that? Active engagement.
Active engagement is non-negotiable. And one of the most effective techniques highlighted in the sources is the brain dump.
The brain dump, how does that work?
So after you watch a 20-minute module on, say, cloud storage, you pause the video. You take a completely blank sheet of paper, and you force yourself to write down everything you can remember without looking at your notes.
Oh man, that sounds excruciating. Because you just realize how much you instantly forgot.
It is painful, but that's the point. It highlights your knowledge gaps immediately. It forces your brain to struggle, and that struggle is the actual biological mechanism of learning.
Wow, okay. I definitely want to dig into flashcards too, because almost everyone uses them, but from what the sources say, almost everyone uses them wrong.
Yeah, they really do.
Usually people just have a binary system, right? A right pile and a wrong pile.
And the problem with that binary system is that it completely ignores latency.
Latency. What do you mean by that in this context?
Well, say you flip a flashcard that says Amazon S3, and it takes you 45 seconds of mental gymnastics to finally remember that it stands for Simple Storage Service and that it's used for object storage.
Okay, yeah, I've been there.
Right, and then you put it in the right pile. Because technically you got it right. But in a timed exam scenario, you do not have 45 seconds to dedicate to basic recall.
Ah, I see. You're eating up precious time.
Exactly. So you need to sort your flashcards by the speed of recall. You need a third pile for correct but slow.
Oh, that's smart. So the goal is to eventually get every single card into a pile that represents instant automatic recall.
Yes. When you see a service name, the definition should just fire in your brain instantly. No hesitation.
Okay, let's talk about practice exams, because I've seen people fall into a massive trap here.
Oh, the memorization trap.
Yes, they take a practice exam, they score 60%, and then they review the answer key just to see that, oh, question 14 was option C and question 22 was option A. Then they retake the exact same test, score 95%, and walk around thinking they're totally ready.
That is literally the fastest way to fail the real CLF-C02. If you do that, you are not learning AWS. You are just memorizing a specific practice test.
Right, and the real exam pulls from a vast dynamic question bank. It's not going to be the same test.
Exactly.
So what is the actual protocol for reviewing a practice test? How do we use them right?
You have to reverse engineer the questions.
Yeah.
When you get a question wrong, just reading why the correct answer is right is only half the job.
So I have to look at the wrong answers too.
You have to read the explanations for the 3 incorrect answers and understand exactly why they are wrong in that specific context.
Okay, give me an example of that just to make it concrete.
Sure. Let's say a question asks, which service is best for querying data directly in Amazon S3 using standard SQL? And, you might guess Amazon RDS.
Which is the relational database service, right?
But the correct answer is Amazon Athena. Now, you need to understand exactly why RDS is wrong in this context.
Okay, why is it wrong?
Because RDS requires you to provision a server and import the data into a structured database first, whereas Athena is completely serverless and just queries the flat files directly where they sit in S3.
Ah, gotcha. So understanding the why behind those incorrect options is what actually builds that deep architectural knowledge.
Precisely.
I also saw a really interesting study hack using AI in one of the community guides.
Oh, yeah, using ChatGPT or a similar LLM is an interactive tutor. It's a great tool.
But there is a strict rule for this to be effective, right?
Yeah.
You must write your own answer first.
Yes, that is crucial. So you take an exam objective like explain the shared responsibility model. You write your explanation down from your own brain. Then you prompt the AI. You say, act as an AWS instructor, review my explanation of the shared responsibility model, tell me what I missed, and clarify any misunderstandings.
That is incredibly powerful. It provides personalized, immediate feedback on your exact blind spots.
It's like having a private tutor sitting right next to you.
Amazing. All right, so we have the study mechanics locked down. We know how to approach the battlefield. Now let's actually look at what we are fighting for.
Let's dive in.
Let's pivot to the foundational philosophy of AWS. Why do businesses actually care about this enough to migrate everything?
This is where we get into domain one, cloud concepts and economics. This makes up roughly 24% of the exam, and it is entirely focused on the value proposition.
Right, because before a company cares about what kind of database you are using, the chief financial officer wants to know how this impacts the bottom line.
Exactly. And that always comes down to the shift from capital expenses or CapEx to operational expenses or OpEx.
Let's define the actual mechanics of that shift. Start with CapEx.
Okay, CapEx involves spending money up front on physical assets. You're buying hardware, actual servers, massive cooling systems, physical real estate to house it all.
And the problem with CapEx and IT is that technology depreciates really rapidly, right?
It depreciates fast, and more importantly, it requires you to predict the future.
Forecasting, which is basically guessing.
Pretty much. Say you're launching a new mobile app. You have to guess how many users you'll have on day one. If you guess you need 10 servers, and then the app suddenly goes viral and 1 million people log on.
Your 10 servers literally melt down, the app crashes, and you lose your one shot at success.
Exactly. Or you try to play it safe. You spend massive amounts of capital to buy 100 servers up front, just in case you go viral.
Yeah.
But your app only gets a modest following, and you only ever end up using 10 servers.
Ouch. So now you have 90 really expensive servers just sitting idle.
Yep. And you are paying for the electricity to run them, the air conditioning to cool them, and the IT staff to maintain them. This is what we call the total cost of ownership, or TCO. And it acts like a massive financial anchor on a company.
So the cloud introduces OpEx, operational expenses. How does that fix the anchor?
OpEx means you pay for what you use exactly when you use it. You don't buy the servers at all. You just rent computing power by the hour, or sometimes even by the second.
So if my app goes viral in that scenario,
AWS automatically provisions 90 more virtual servers for you instantly. And then when the viral spike ends on Monday morning, AWS terminates those 90 servers and you instantly stop paying for them.
it's literally like taking a ride share instead of buying a fleet of cars. You only pay for the distance you travel, and you aren't responsible for the maintenance or the oil changes or paying for the garage space.
That's a perfect analogy. It completely eliminates the guesswork of capacity planning.
But to actually achieve those financial benefits, you have to build your applications differently, don't you? You can't just move old stuff over and expect it to be cheaper.
No, you really can't. If you take an old monolithic application from an on-premises data center and just copy-paste it into the cloud,
Yeah.
you will not save money. In fact, it might even cost you more.
Really? So what do you have to do?
You have to adhere to core cloud design principles.
Okay, let's go through those. The first principle always sounds so counterintuitive to me. It's design for failure. Why would an architect actively assume their new system is going to break?
Because it's a statistical inevitability. I mean, at a certain scale, hardware fails. Hard drives corrupt, network switches burn out, power grids fluctuate, cables get accidentally cut by construction crews.
So if you assume your hardware is infallible, A single failure just takes down your entire business.
Exactly.
So how do you design for failure in a practical sense? What does that look like?
You use redundancy. Instead of running your entire database on one massive, incredibly expensive virtual server, you run it across multiple smaller servers located in different physical data centers.
Oh, I see. So if one data center gets hit by a localized power outage?
The other servers instantly pick up the load, and the end user never even notices a disruption. That's designing for failure.
That makes a lot of sense. And that ties directly into the next principle. Decouple your components. I want to spend some real time on this because tightly coupled versus loosely coupled is a huge concept on this exam.
It is massive. Let's use a real-world e-commerce example to break it down. In a tightly coupled, monolithic architecture, your web server, your inventory database, and your payment processing system are all completely fused together.
Right. So if a user clicks buy, the web server talks directly to the payment system.
Exactly. But what happens if the payment system is down for maintenance? Or it just gets overwhelmed with traffic and freezes?
Well, the web server is going to wait for a response it will never get. It times out, the user gets an ugly error page, and the entire website effectively crashes.
Right. A failure in one component cascades and destroys the whole system. That's tight coupling.
So decoupling solves this. How? What's the mechanism?
By introducing a buffer between the components. In AWS, this is often done using a message queue, like Amazon SQS, which stands for Simple Queue Service.
Okay, so how does SQS change the flow?
Now, when a user clicks buy, the web server doesn't talk to the payment system directly at all. Instead, it drops a message into the SQS queue that just says, process order number 123, and it immediately goes back to serving the user.
And what's the payment system doing?
The payment system is just reading from that queue at its own pace. This is an asynchronous process.
Oh, wow. So if the payment system crashes for 10 minutes, the website doesn't crash.
Exactly. The web server just keeps working, dropping orders into the queue. And when the payment system comes back online, it looks at the queue, sees a backlog of messages, and just starts processing them one by one. The components are totally independent.
That is a brilliant mechanism. The web front end stays responsive regardless of what's happening in the back end.
It's a game changer for reliability.
Now, let's talk about how we handle fluctuating traffic. We need to distinguish between two specific types of scaling: vertical scaling and horizontal scaling. I know this is a classic exam topic.
It is, and it trips a lot of people out. Scaling is just how you adjust your resources to meet demand. Let's start with vertical scaling, which is also known as scaling up.
Okay, scaling up.
This means taking an existing server and increasing its internal specifications. Say you shut down a server with 8 gigabytes of RAM, and you turn it back on as a server with 64 gigabytes of RAM and a way faster CPU.
But there's a physical limit to that, right? Like, I can't just infinitely add RAM to a single machine. Eventually, I hit the physical ceiling of what a motherboard can actually support.
Precisely.
Plus, you usually have to take the server offline to upgrade it, which means downtime.
Right, and nobody wants downtime. That is why the cloud heavily favors horizontal scaling.
Which is scaling out.
Yes. Instead of making one server bigger, you just add more servers to the pool. So if one server can handle 1,000 users, and you suddenly have 5,000 users, you don't upgrade the server, you just spin up 4 more identical servers.
And then use a load balancer to distribute the traffic evenly among all 5 of them.
Exactly. It's like instead of adding another floor to your house vertical scaling, you just build 5 more identical houses next door horizontal scaling.
I love that analogy. And this pairs perfectly with the concept of elasticity. But elasticity isn't just the ability to scale, right? It's the automation of scaling, both out and in.
That's a really crucial distinction for the exam. Elasticity uses metrics to trigger horizontal scaling automatically. You can set a rule that says, hey, if the average CPU utilization across my servers hits 80%, automatically launch 2 more servers.
But the in part is just as important.
Right. You also set a rule that says if the average CPU drops below 30%, terminate 2 servers.
Yeah.
That automated shrinking is what actually fulfills the OpEx promise of only paying for what you need.
Got it. Now, to put all these principles together, AWS actually formalized them into something called the well-architected framework.
Yes, the well-architected framework. It is a set of best practices divided into 6 pillars. And if you want to pass the exam, you need to understand the fundamental goal of each pillar.
Okay, let's walk through the mechanics of each one. Number 1 is operational excellence.
Right. And this isn't just about keeping the lights on. It's about using coding to automate your deployments. It's about monitoring your systems so you actually know about problems before your customers call you complaining. And it's continuously improving your processes based on real data.
Okay, number 2, Security. I mean, this feels obvious, but what's the AWS definition?
Security is paramount. It means encrypting your data at rest and in transit, managing user identities with extreme prejudice, and actively protecting your systems from external threats.
Number 3, reliability. This goes back to what we just talked about with designing for failure, right?
Exactly. Can your system automatically recover from a database crash? Does it gracefully handle the loss of a network connection? That's reliability.
The number 4 is performance efficiency. This one is interesting to me. It's about not using a sledgehammer to drive a nail.
That's a great way to put it. It's about choosing the right tool for the job. If you just need to store flat image files, you shouldn't put them in an expensive relational database. You should use a cheap object storage service.
Right, be efficient with your tech choices. Number 5, cost optimization.
This is the continuous process of analyzing your AWS bill. Are you paying for servers that have zero traffic? Are you using the most cost-effective pricing model? It's all about eliminating waste.
And then the newest one, number 6, sustainability.
Yes, this is about minimizing the environmental impact of your cloud workloads. It means writing efficient code that requires less computing power, which thereby consumes less electricity. It's about the shared responsibility for carbon footprints.
Okay, so a company understands the well-architected framework, they want the OpEx model, they get the pillars. How do they actually get their stuff into the cloud? The exam tests on migration tools, specifically mentioning the Cloud Adoption Framework, or CAF, and a very unique physical tool called AWS Snowball.
Let's start with CF. The Cloud Adoption Framework is mostly business guidance. It really helps organizations align their IT strategy with their business goals before they actually migrate. It's planning.
Okay, but what about the actual data? Because moving data is hard.
It is. And AWS Snowball solves a massive physics problem. Imagine a hospital with a legacy data center holding 50 petabytes of high-resolution medical imaging data.
50 petabytes. I mean, if they tried to upload 50 petabytes over a standard corporate internet connection, it would literally take years. The connection would time out, data would get corrupted. It's functionally impossible.
Right, you cannot beat the speed of a physical truck on a highway. So AWS literally mails the hospital a ruggedized, tamper-proof physical storage appliance called an AWS Snowball. It looks like a heavy-duty metal briefcase.
And they just plug it in.
Yep. The hospital plugs it directly into their local network, transfers the data at blazing local network speeds, and then physically ships the briefcase back to AWS.
And then AWS takes it, plugs it straight into their core network, and uploads it directly to the cloud. It is the ultimate example of a physical solution to a digital bottleneck.
It bypasses the internet entirely.
Wow.
It's faster. And because the data is heavily encrypted on the device and tracked via GPS, it's incredibly secure.
Which brings us perfectly to our next major topic. We understand the economics now, but the absolute first question any CEO or chief risk officer asks before migrating to the cloud is, if my data is on someone else's servers, is it actually safe?
Exactly. Welcome to Domain 2, Security and Compliance. This is roughly 30% of the exam, and the foundational concept you absolutely must master here is the AWS shared responsibility model.
Because that dictates exactly who is on the hook when something goes wrong.
Yes. A lot of people just assume that because they are using AWS, Amazon is completely responsible for keeping them from getting hacked.
Yeah, I feel like that's a super common misconception.
It's a dangerous career-ending assumption, honestly. The model draws a very hard line. And the easiest way to remember it for the test is this. AWS is responsible for security of the cloud. The customer is responsible for security in the cloud.
Okay, let's dissect security of the cloud. What are the actual mechanisms AWS manages?
AWS secures the physical and foundational infrastructure. So they are responsible for the physical security of the data center buildings. They manage the biometric locks, the security guards, the perimeter fences. They are responsible for the cooling systems, the power generators, and the physical network cables.
They also manage the hypervisor, right? The software that creates the virtual machines.
Yes. They ensure that if you rent a virtual server, and a competitor rents a virtual server on the exact same physical piece of hardware, your competitor cannot break out of their virtual environment and access your data. AWS guarantees that isolation.
Okay, so the physical foundation is rock solid. What about security in the cloud?
That is entirely on you. You are responsible for your data. You decide whether or not to encrypt it. You are responsible for configuring your network firewalls. If you provision an EC2 virtual server, you choose the operating system, which means you are responsible for installing security patches and updates.
It's literally like renting an apartment.
That's a good way to put it.
Yeah, like The landlord, which is AWS, is responsible for the structural integrity of the building, the locks on the main lobby door, and ensuring the plumbing doesn't leak. They secure the building. But if you, the tenant, leave your specific apartment door wide open and you leave your laptop sitting on the kitchen counter for anyone to steal, well, you can't blame the landlord. You failed to secure what was inside your apartment.
That analogy works perfectly. But the exam will test you on a critical nuance here. The line of responsibility actually shifts depending on the type of service you're using.
How so?
Well, the apartment analogy assumes you are renting a raw, empty apartment, which is exactly like renting a raw EC2 instance. You manage everything inside. But let's say you use a managed database service like Amazon RDS.
Okay, so it's not raw anymore.
Right. You aren't renting a raw server. You are renting a fully functioning database.
Yeah.
Because it's a managed service, AWS takes on more responsibility. AWS will automatically install the operating system patches. AWS will handle the database software updates.
So my responsibility shrinks. But I assume I still have to manage who can actually access the database, and I have to configure the password policies.
Exactly. You always control access. And if you go all the way to a serverless architecture like AWS Lambda, AWS manages almost everything underlying the service. Your only real responsibility at that point is the security of your application code itself, and again, the access permissions. The more managed the service, the more responsibility AWS assumes.
Speaking of access permissions, let's dive into IAM, Identity and Access Management. This feels like the nervous system of AWS security.
It absolutely is. IAM is how you authenticate meaning, prove who you are and authorize meaning, prove what you are allowed to do within your entire AWS environment.
And the first rule of IAM, which I know is guaranteed to be tested, revolves around the root user account. Let's talk about that.
So when you first sign up for AWS with an email and password, that is the root user. It has unrestricted God-level access to everything in the account. You can delete massive databases, spin up expensive server farms, change billing details, close the account.
Which is why everyday use of the root user is a massive security violation.
Huge violation. Best practice dictates that the moment you create an account, you lock the root user down immediately, you create a complex password, you enable multi-factor authentication or MFA, and you virtually bury that account.
But wait, if I lock away the root user, how do I actually get any work done?
You use the root account exactly one time to create an IAM user for yourself. You grant that specific IAM user administrative privileges, and you use that account for your daily tasks.
Ah, I see.
Yeah, because if your IAM user gets compromised, you can use the locked away root account to delete it and regain control. But if the root account gets compromised, your entire business is severely, maybe permanently compromised.
Wow. Okay, and this plays directly into the principle of least privilege, too.
Yes, very heavily tested. When you create an IAM user for a new employee, you do not give them access to everything. You only grant them the absolute minimum permissions required to do their specific job.
So if a junior developer only needs to read files from a specific storage bucket, you give them read-only access to that one specific bucket. You do not give them write access, and you certainly don't give them access to the databases.
Exactly. It limits the blast radius. If that junior developer accidentally runs a malicious script, or if their laptop gets stolen at a coffee shop, the attacker only has access to that one specific bucket, not your entire corporate infrastructure.
Right, it contains the damage. Now, beyond IMM, Domain 2 covers a pretty wide array of specific security services. This is where people get really overwhelmed, like an alphabet soup of services. But let's break them down by mechanism.
Good plan.
Let's start with AWS Way. What is the actual mechanism here?
WAF stands for Web Application Firewall. It operates at the application layer. Think of it as a highly trained bouncer at the door of your website who is inspecting everyone's ID very closely.
So not just checking if they have an ID, but looking for forgeries.
Exactly. WAF inspects the actual content of the incoming HTTP requests. It's looking for known malicious patterns, like SQL injection, where an attacker tries to sneak database commands into a login field, or cross-site scripting. If WAF sees those specific malicious patterns in the request, it just blocks the traffic before it ever reaches your web server.
Okay, so WAF inspects the content. How is that different from AWS Shield?
Shield doesn't care about the content of the request at all. It only cares about the volume. Shield is designed to protect against distributed denial of service, or DDoS attacks.
And a DDoS attack is when an attacker uses a botnet of thousands of compromised computers to flood your website with junk traffic, just overwhelming your servers until they crash.
Right, so if WAF is the bouncer checking IDs, Shield is crowd control. If 50,000 people suddenly rush the door at the exact same millisecond, the bouncer gets crushed.
Makes total sense.
Shield detects that massive, unnatural spike in traffic volume and automatically reroutes it into a sinkhole, scrubbing the junk traffic while allowing legitimate users to still access your site. And importantly for the exam, Shield Standard is enabled by default for all AWS customers for free.
Okay, next we have Amazon Inspector.
Inspector is an automated vulnerability management service. Its mechanism is scanning. You run Inspector against your EC2 instances or your container images. It scans the operating system and the installed software, comparing them against a massive database of known security vulnerabilities like CVEs and network exposure issues.
So it's literally like a building inspector walking around looking for cracks in the foundation or exposed wiring, and then it just hands you a prioritized list of things you need to patch.
Precisely. Now, contrast that scanning approach with Amazon Guard Duty. Guard Duty is not a scanner. It is a continuous monitoring service powered by machine learning and anomaly detection.
How does it actually detect an anomaly?
It quietly analyzes billions of events across your AWS account, things like network traffic logs and API calls. It establishes a baseline of what normal looks like for your specific business. So if your developers usually log in from Chicago during normal business hours, that's normal.
But if suddenly an IAM user logs in from a known malicious IP address in another country at 3 a.m. and tries to export an entire database,
Guard Duty flags that as highly anomalous and generates a critical alert. It's intelligent threat detection.
Okay, so if I have Inspector scanning for patches and Guard Duty looking for anomalies and WAF blocking web attacks, I have security alerts firing off in 10 different directions. That sounds messy.
Which is exactly why AWS created Security Hub. Security Hub is a central dashboard. It adjusts all the findings from Inspector, Guard Duty, Macy, and even third-party partner tools and aggregates them into a single pane of glass. It gives you a comprehensive view of your overall security posture and helps you prioritize exactly which fires to put out first.
The last tool in this section is completely different in mechanism, and that's AWS Artifact.
Yes, Artifact is not a defensive tool at all. It is an auditing and compliance portal. Say you are a healthcare company handling patient data. You are legally required to comply with HIPAA. Your auditors will demand proof that the underlying AWS infrastructure is actually secure.
So you go to AWS Artifact to download the official third-party audit reports and security certifications that prove AWS is maintaining compliance on their end of the shared responsibility model.
It's basically the digital filing cabinet for legal compliance.
Perfect. Now, before we leave security, we have to talk about a tool that bridges security, performance, and cost. And that is AWS Trusted Advisor.
Trusted Advisor is one of the most highly tested services on the entire exam. You have to know it. It acts as an automated, always-on cloud consultant. It continuously inspects your AWS environment and compares it against AWS best practices across 5 distinct categories.
What are the 5 categories?
Cost optimization, security, performance, fault tolerance, and service limits. For example, under security, it will actively flag you if you have an S3 bucket that is accidentally left completely open to the public internet.
Which happens a lot.
Too often. And under cost optimization, it'll identify EC2 instances that have had 0 CPU utilization for 2 weeks and suggest you turn them off to save money.
So it's proactively scanning your architecture to make sure you aren't making silly, expensive, or dangerous mistakes. I love that.
It's an essential tool.
All right, we've locked the doors, we've set the alarm system, now we actually have to build the house. We are moving into the largest portion of the exam, roughly 34%, Domain 3, Cloud Technology and Services.
This is where we categorize the actual architectural building blocks. And we have to start with the physical reality of the cloud, the global infrastructure. Because AWS is not just a nebulous fog, it is a massive network of physical data centers distributed all around the world.
And the highest level of this infrastructure is the region, correct?
A region is a specific physical geographic area in the world. Examples include Northern Virginia, which is the Southeast 1, or London, US 2, or Tokyo up Northeast 1. When you launch a server or create a database, you must choose exactly which region it lives in.
But why does the region matter? Why not just put everything in Virginia and call it a day?
2 main reasons. Latency and compliance. If your customer base is entirely in Japan and your server is in Virginia, every single time they click a button on your app, the data has to travel across the Pacific Ocean and back. That causes noticeable delay or latency. You put the server in Tokyo to be physically closer to the user so it's fast.
And the second reason is compliance.
Data sovereignty. Some countries have really strict laws dictating that citizens' data cannot legally leave the country's borders. If you operate a bank in Germany, you might be legally required to use the Frankfurt region.
Okay, that makes sense. And inside a region, we have availability zones, or AZs. And this goes back to designing for failure.
Exactly. An availability zone is a cluster of one or more discrete data centers within a region. The critical mechanism here is physical separation. The AZs in a given region are separated by a meaningful physical distance, usually tens of miles.
Why tens of miles? Why not just put them right next door? Or why not hundreds of miles apart?
Well, if they are right next door to each other, a single localized disaster like a massive flood, a tornado, or a catastrophic power grid failure could take out both data centers at once. Tens of miles of separation ensures they are on different floodplains and completely different power grids.
But they can't be hundreds of miles apart either.
No, because AWS connects the AZs with high-speed dedicated fiber optics. They need to be close enough that data can replicate synchronously between them with single-digit millisecond latency. If they were hundreds of miles apart, the lag would be too high for real-time database replication.
So, to achieve high availability, I designed my application to run across multiple AZs. If AZ-A gets hit by a tornado and goes completely dark, my servers in AZ-B are physically unaffected and they just continue serving customers.
Yes, high availability is all about using multiple AZs. And finally, we have edge locations. These are much smaller data centers, and there are hundreds of them spread globally, far more than there are regions. They act as caching endpoints for Amazon CloudFront, which is AWS's Content Delivery Network, or CDN.
How does caching actually work in this context?
So if your main server is in Virginia and a user in Sydney wants to download a large video from your site, pulling it all the way from Virginia is slow. With CloudFront, the first time a user in Sydney requests the video, AWS pulls it from Virginia, delivers it to the user, and then saves a copy, caches it at the edge location in Sydney.
Oh, so the next time another user in Sydney wants that exact same video.
They just download it straight from their local edge location in Sydney, which is lightning fast. It never goes back to Virginia.
Okay, so that's the physical map of the world. But how do I actually control these data centers from my laptop sitting at home?
You have several interfaces. The most common for beginners is the AWS Management Console. This is a web-based graphical interface. You point, you click, you use drop-down menus to launch services. It's very intuitive, but it is heavily manual.
Right, so if I need to deploy 100 servers configured exactly the same way, clicking through the console 100 times is insanely inefficient and prone to human error.
Which is exactly why developers use the AWS CLI, the command line interface. You type text commands directly into a terminal. You can write a quick script that loops a command 100 times, deploying 100 servers in seconds. You also have SDKs, software development kits, which allow you to interact with AWS services directly from within your application code using languages like Python, Java, or Node.js.
But the gold standard for cloud architecture, and something the exam will definitely test, is infrastructure as code, or IAC, using services like AWS CloudFormation.
Infrastructure as code is a massive paradigm shift. Instead of manually clicking buttons or running individual commands, you write a text file, a template, that declares your entire desired architecture. You literally write code that says, I want a VPC, 2 subnets, 3 EC2 instances, and a database. You feed that template to CloudFormation, and AWS automatically provisions the entire environment exactly as specified.
The mechanism of IAC means your infrastructure is now perfectly repeatable. If I want an exact replica of my production environment to use for testing, I don't have to rebuild it manually. I just run the exact same code template again.
It's version controlled, auditable, and it completely eliminates manual misconfiguration.
Let's move into the actual services you are provisioning, starting with compute. The heavyweight here is obviously Amazon EC2, Elastic Compute Cloud.
These are the virtual servers. We've talked about them a lot. You pick the OS, the CPU, the RAM, and you have total control. But managing an entire operating system is heavy. That brings us to containers. What exactly is the mechanism of a container?
Yeah, how does it differ from a virtual machine?
A traditional virtual machine, like an EC2 instance, requires a full, heavy operating system to run. A container is a much lighter way to package an application. It bundles the application code with its specific dependencies and libraries, but it actually shares the underlying operating system kernel with other containers on the host.
So it's much faster to start up, it uses way fewer resources, and it solves that classic developer problem of, well, the code worked on my laptop. Because the container includes the exact environment, it runs identically on a laptop or in the AWS cloud.
Exactly. AWS offers 2 main orchestration services to manage thousands of containers. Amazon ECS, Elastic Container Service, which is AWS's proprietary system, and Amazon EKS, Elastic Kubernetes Service, for those who prefer the industry-standard open-source Kubernetes.
But even with containers, I still have to manage the underlying server clusters that they run on, don't I? What if I want literally zero server management?
Then you move to serverless compute. AWS Fargate is a serverless compute engine specifically for containers. You just give AWS your container and they figure out all the underlying servers. But the absolute crown jewel of serverless compute is AWS Lambda.
Lambda is event-driven computing. Explain how that works because it's fascinating.
With EC2, the server runs 24/7 waiting for a request, and you pay for every single hour it runs, even if no one is using it. With Lambda, you write a piece of code, a function, and you upload it. The code does absolutely nothing until it is triggered by an event.
What kind of event?
Could be anything. A user uploading a photo to an S3 bucket, a modification to a database record, an HTTP request from a web gateway. When the event occurs, AWS instantly provisions a tiny, invisible compute environment, executes your code, and then immediately destroys the environment.
And the OpEx billing mechanism here is incredible. You don't pay by the hour, you pay for the exact milliseconds your code takes to execute. If your function doesn't run for a week, your compute bill for that week is literally zero.
It is the ultimate expression of the cloud economics we talked about earlier.
All right, to tie all these compute resources together, we need networking. The foundational boundary is the Amazon VPC Virtual Private Cloud.
This is your private, logically isolated section of the AWS cloud. It's like a fenced-off neighborhood where you control all the gates.
Inside the VPC, you divide your network into subnets. And subnets are tied to specific availability zones, right?
Yes. The mechanism here is routing. You can have public subnets, which have a route to an internet gateway, allowing resources inside, like your web servers, to communicate directly with the public internet.
And private subnets, which have absolutely no route to the internet. This is where you put your highly sensitive databases. Even if an attacker somehow finds the IP address, they physically cannot route traffic to it from the outside world.
Exactly. And you control the traffic flow between these subnets using two main firewalls. Network Access Control Lists, or NACLs, act as a firewall at the broader subnet level. Security groups act as a firewall at the individual instance level.
So if a bad request gets past the NACL into the subnet, the security group around the specific EC2 instance can still block it. It's defense in depth.
Yeah.
Now, how do users actually find my network? They don't type in an IP address, they type a domain name.
Which brings us to Amazon Route 53. This is AWS's highly available domain name system, or DNS service. DNS is basically the phone book of the internet. It translates a human-readable domain, like example.com, into the machine-readable IP address, like 192.0.2.1, so computers can connect. Route 53 routes your global users to your AWS resources.
There is one very specific networking service I want to highlight because it comes up in enterprise migrations a lot. AWS Direct Connect. If a massive bank is moving to AWS, they probably don't want their sensitive financial data traveling over the public internet to get there, even if it is encrypted.
The public internet is chaotic. Traffic bounces through multiple ISPs, bandwidth fluctuates wildly, and latency is unpredictable. AWS Direct Connect solves this by establishing a dedicated physical network connection, usually a massive fiber optic cable, from your on-premises data center directly into an AWS facility.
It completely bypasses the public internet. It's a private highway straight to the cloud. This provides massive, consistent bandwidth and vastly improves security.
Okay, so we have servers and networks. Now we need to store the data. Storage services. The exam absolutely requires you to know the fundamental difference in the mechanisms of S3, EBS, and EFS.
Let's break them down. Start with Amazon S3 Simple Storage Service.
S3 provides object storage. Do not think of this like the hard drive on your laptop. Think of it as an infinitely scalable digital warehouse. S3 is a flat namespace. You don't have deeply nested folders. You have buckets, and you drop objects, which are files, into those buckets.
Objects being things like photos, videos, backup files, or static website assets.
Yes. Each object has the data itself, metadata, which is information about the data, and a unique key or identifier. You access these objects via web APIs over the internet. But the catch is, you cannot install an operating system on object storage. It doesn't support the rapid, block-level read and write operations an OS needs to function.
Which is exactly why we need Amazon EBS Elastic Block Storage.
It's exactly. EBS is block storage. This is the literal virtual hard drive that you attach to your EC2 instance. When you install Windows or Linux, you install it onto an EBS volume. Block storage divides data into fixed-size blocks, allowing for the incredibly fast random read-write access required by operating systems and traditional databases.
But there is a limitation with EBS. Usually, an EBS volume can only be attached to one single EC2 instance at a time. It's like plugging a physical USB drive into a laptop, only that one laptop can read it. What if I have 10 different web servers and they all need to read and write to a centralized pool of files simultaneously?
Then you need file storage, specifically Amazon EFS Elastic File System. EFS acts like a managed network-attached storage, or NAS drive. You can mount a single EFS file system to dozens or even hundreds of EC2 instances simultaneously across multiple availability zones.
So just to summarize for the listener, S3 is the infinite warehouse for objects. EBS is the fast, dedicated hard drive for a single server. EFS is the shared network drive for many servers.
Spot on. And there's one more storage tool to mention, Storage Gateway.
Oh, right. Storage gateway. What's the use case there?
It bridges the gap between on-premises and the cloud. If your local data center is running out of physical storage space, you install a Storage Gateway virtual appliance locally. To your local servers, it looks and acts exactly like a normal local hard drive. But behind the scenes, it is asynchronously uploading that data into Amazon S3. It provides virtually unlimited cloud storage while maintaining local performance.
Okay, let's move from raw files to structured data, database services. We need to define the mechanisms here clearly.
If your application requires complex queries, strict data integrity, and uses tables with rows and columns, you need a relational database. You use Amazon RDS, the Relational Database Service. RDS manages traditional engines like MySQL, PostgreSQL, or SQL Server. AWS handles the backups and patching for you.
But if a company wants the absolute pinnacle of relational database performance built specifically for the cloud, they don't use standard RDS, do they?
No, they use Amazon Aurora. Aurora is a proprietary relational database engine created by AWS. It is fully compatible with MySQL and PostgreSQL, but it totally separates the compute engine from the storage layer. The storage automatically scales and replicates 6 times across 3 availability zones. It is highly fault-tolerant and significantly faster than traditional engines.
What if my data doesn't fit neatly into a rigid table? What if I am building a high-traffic mobile game where user profiles change dynamically and I need massive horizontal scalability?
Relational databases really struggle to scale horizontally. For that, you need a NoSQL or non-relational database.
No.
Amazon DynamoDB is a fully managed, serverless NoSQL key-value database. It provides single-digit millisecond performance at virtually any scale.
And it doesn't use complex SQL queries, right? You just request a key and it instantly returns the value.
Yes. Simple, fast, infinitely scalable. And if you need even faster performance, say microsecond latency for a real-time gaming leaderboard or a financial trading platform, you use an in-memory database. Amazon Elasticache allows you to deploy Redis or Memcache to cache frequently accessed data directly in RAM rather than reading it from a slower disk.
Okay, to round out domain 3, we have AI, machine learning, and analytics. We aren't just storing data anymore, we are extracting value from it. Let's explain how these actually function. Start with analytics. If I have a mountain of raw data sitting in my S3 warehouse, how do I actually analyze it?
Well, the traditional way would be to provision a huge database, write a script to extract all the data from S3, load it into the database, and then query it. It takes hours, sometimes days. Amazon Athena changes that mechanism entirely.
How does Athena work?
Athena is completely serverless. You just point it at your S3 bucket, write a standard SQL query, and it analyzes the flat files exactly where they sit. You pay only for the data scan during the query. It's instant analytics.
That's incredibly powerful. But what if I am dealing with a continuous, massive flow of real-time data? Say I'm tracking clickstream data from millions of users on a website or telemetry data from 1 million IoT sensors on factory machines. A traditional database would just drown under that fire hose of data.
You need a buffer. Amazon Kinesis is designed to ingest and process real-time streaming data. Think of it as a massive, highly durable sponge. It absorbs the fire hose of millions of data points per second, holds them in a stream, and allows your analytics applications to consume and process that data at a manageable pace without crashing.
Awesome. And if I have a massive data processing job using big data frameworks like Hadoop or Apache Spark, I would use Amazon EMR, Elastic MapReduce. And to visualize all this data to create those beautiful business intelligence dashboards for the executives, I use Amazon QuickSight.
Moving to machine learning. The flagship service for data scientists is Amazon SageMaker. Building a machine learning model traditionally is a really disjointed process. You have to gather data, prep the infrastructure, write the algorithm, train the model on massive GPUs, and then figure out how to deploy it to an app. SageMaker provides a fully managed, unified environment to build, train, and deploy models seamlessly in one place.
And AWS offers pre-trained AI services for developers who don't know machine learning, right? For example, Amazon Lex. Lex is the exact same deep learning engine that powers Amazon Alexa, but packaged as an API. You can use it to build sophisticated conversational chatbots or voice interfaces directly into your own applications without knowing any AI math.
Okay, we have covered a massive amount of architecture, which brings us to the final hurdle, Section 5, Domain 4 Billing, Pricing, and Support. This is 12% of the exam.
We've built a highly available, secure, decoupled architecture. Now the CFO is knocking on the door wanting to know how we actually pay for it. We established earlier that the cloud is OpEx, but the mechanism of how you pay for compute capacity dictates your ultimate savings. Let's break down the EC2 pricing models.
There are 4 distinct models you need to know. The first is on-demand. This is the default. You pay by the hour or the second. There is zero upfront commitment, and you have ultimate flexibility. You can spin up a server, run it for 15 minutes, and terminate it.
It's perfect for unpredictable workloads or short-term experiments, but mathematically, on-demand has the highest hourly rate. If I know absolutely that my core database server needs to run 247 for the next 3 years, on-demand is a terrible financial decision.
Exactly. That is when you pivot to reserved instances or savings plans. The mechanism here is commitment. You sign a contract committing to a specific amount of compute usage over a 1-year or 3-year term. Because you guarantee AWS that revenue, they grant you a massive discount, often up to 72% off the on-demand price. You trade flexibility for deep financial savings.
The third option is the most unique, and it requires a very specific architectural mindset: spot instances.
AWS operates at a mind-boggling scale, meaning they always have massive amounts of spare server capacity just sitting idle. An idle server generates zero revenue. To incentivize use, AWS offers this spare capacity as spot instances at staggering discounts, up to 90% off the on-demand price.
But there is a massive catch, right?
The catch is that AWS can reclaim that capacity at any time. If overall demand spikes and a customer willing to pay the full on-demand price needs a server, AWS will terminate your spot instance with only a 2-minute warning. It's like buying a standby ticket for a flight. You get a cheap seat, but if a full-paying passenger shows up, you get bumped.
Which dictates how you use them. You would never put a critical user-facing web server on a spot instance. If it gets terminated, your website goes down. Use spot instances for fault-tolerant batch processing workloads.
Right. Say you need to render 10,000 frames of an animated movie. You spin up 100 spot instances. If AWS terminates 10 of them halfway through, it doesn't break the system. The remaining frames just go back into an SQSQ and get processed later by another server.
The final model is dedicated hosts.
In a normal cloud environment, you use a multi-tenant model. Your virtual server might be running on the same physical piece of silicon as my virtual server. The hypervisor keeps them isolated. However, some highly regulated industries prohibit multi-tenancy entirely. Or a company might have legacy software licenses that are legally bound to physical server sockets, not virtual cores. A dedicated host gives you an entire physical server dedicated exclusively to your use. It is the most expensive option, but it solves specific compliance and licensing constraints.
Okay, beyond just EC2, how do businesses manage their overall cloud spend? The exam expects you to know the difference between 3 specific billing tools: AWS Budgets, AWS Cost Explorer, and the AWS Pricing Calculator.
You need to understand their temporal focus: past, present, and future. Let's start with the future. If you are an architect pitching a brand new project, you haven't built anything yet, but management wants a cost estimate. You use the AWS Pricing Calculator. You input your expected architecture: 3 EC2 instances, a 500 gigabit RDS database, and 2 TB of S3 storage, and it predicts your monthly bill.
Now for the present. We build the project. I want to make sure the team doesn't accidentally spin up expensive servers and blow our budget. I need to set guardrails.
You use AWS Budgets. Budgets is proactive. You set custom spending limits. If you set a budget of $1,000 for the month, and by week 2 your actual spend or your forecasted spend hits $800, Budgets automatically triggers an alert, sending an email or an SNS notification to the team before the massive bill actually arrives.
And finally, the past. I get my monthly bill, and it's way higher than expected. I need to play detective and figure out exactly what service burned the cash.
You use AWS Cost Explorer. This is a reactive, analytical dashboard. You can dive deep into your historical spend, filter by specific services, by region, or by custom tags. You look at visual graphs to identify trends, figure out exactly why costs spiked on a random Tuesday, and find areas to optimize.
Now, what if a company scales massively? An enterprise doesn't just have one AWS account. They might have a separate account for the dev team, the QA team, marketing, and HR just to keep resources isolated. Managing 50 separate billing portals is a nightmare.
AWS Organizations solves this. It allows you to centrally manage and govern multiple AWS accounts. The primary financial benefit highlighted on the exam is consolidated billing.
It rolls all 50 accounts into a single master invoice, but there's a deeper mechanism at play here regarding volume discounts, right?
Yes, economies of scale. Many AWS services, like S3 storage or data transfer, have tiered pricing. The more you use, the cheaper the per gigabyte rate becomes. If the dev account uses 4 terabytes and the QA account uses 4 terabytes separately, they both pay the higher Tier 1 rate. But with consolidated billing, AWS mathematically combines their usage. The organization is billed for 8 terabytes total, which might push the entire company into the cheaper Tier 2 pricing bracket. You save money simply by combining the bills.
That is a critical detail to understand on the test. To wrap up Domain 4, we have to talk about what happens when you need help. What are the support plans?
Every single AWS customer gets basic support for free. This includes access to customer service for billing issues, access to documentation, the Knowledge Center, and AWS Repost, which is a community forum. But if you need technical support to troubleshoot a broken architecture, you need a paid plan.
The tiers are developer, business, and enterprise, right?
Correct. Developer support is for non-production environments. You get business hour email access to cloud support associates. Business support is when you have production workloads running. This gives you 24/7 phone, email, and chat access to cloud support engineers with much faster response times.
And enterprise support.
Enterprise support is for massive, mission-critical workloads. The defining feature that is highly tested is the TAM, the Technical Account Manager. A TAM is a designated AWS expert who acts as your personal concierge, advocate, and architectural advisor within AWS.
If a massive issue occurs, say an entire availability zone seems to be experiencing network packet loss, where do I look to see if it's an AWS problem or my problem?
You check the AWS Health Dashboard. Unlike the general AWS status page, the Health Dashboard provides a personalized view. It looks at the specific resources you are currently running and tells you if any underlying AWS infrastructure issues are actively affecting your specific environment.
And finally, if a company decides they don't have the internal talent to build or migrate their architecture, where do they turn?
They utilize the AWS Partner Network, or APN. This is a global network of vetted third-party companies. Consulting partners will actively help you design and migrate your infrastructure. Technology partners provide commercial software solutions that integrate seamlessly with AWS.
And there it is. We have navigated the entire map. We covered the rigorous study mechanics and test protocols. We broke down the economic philosophies of CapEx versus OpEx. We deeply explored the shared responsibility model and how to lock down your architecture. We dissected the physical global infrastructure, the core compute, networking, storage, and database services, and finally, how to manage the financial reality of it all.
It is a massive ecosystem, but it is logical. The economic desire for OpEx drives the need for elastic architecture. That architecture requires robust shared responsibility security. The security protects a diverse array of services, and the usage of those services feeds directly into billing tools. It all connects.
For everyone listening, you have just absorbed a true masterclass. As you move forward, remember the study strategy. Build that 30-day plan. Force your brain to struggle with the blank page brain dumps. When you take practice exams, meticulously reverse engineer the incorrect answers so you understand the underlying mechanisms.
And as you walk into that exam room, keep the bigger picture in mind. Earning the AWS Certified Cloud Practitioner isn't just about adding a digital badge to your resume or passing a multiple-choice test. You are acquiring fundamental business literacy for the modern era.
Understanding these concepts changes how you evaluate business risk entirely. When you understand the elasticity of the cloud, you realize that the barrier to entry for innovation has never been lower. You don't need millions of dollars in capital to test a brilliant idea. You just need a few dollars and a solid architectural understanding.
It shifts your mindset from managing physical hardware constraints to designing limitless, decoupled, resilient systems. Keep exploring these mechanisms, keep building those mental models, and you will absolutely crush the CLF-C02 exam.
Think back to that massive $10 million data center gathering dust because someone couldn't predict the future. You now have the knowledge to never make that mistake. You have the mat, you understand the mechanics, and you know how to build in the cloud. Now, go ace that test. Keep diving deep.